Insertion Sort. For this algorithm, we're going to start iterating from the element in the index 1, and we are going to compare backwards to the element in the previous index. The element in the previous index is greater than the element in the index 1, then we swap positions. And then we're going to continue to the next element. In this case, in the position in the index 2 is compared to the elements in the previous indexes. So if the elements in the previous indexes are greater than the element in the position 2, this element is going to be swapped until it arrives to the right position where there is no element below it that is greater. And then here is our pseudocode, and here we have two loops, and the maximum time complexities for these loops as n per n. We're traversing up to n-1 elements every time. So n-1 per n-1, we have a polynomial time complexity, and in this case the order is going to be n squared, and it's going to be bounded in the P space, which is considered for this insertion sort the complexity class of P. Now we have the traveling salesman problem. In the traveling salesman problem, we're trying to get from one city to all other cities only once, only pass every time once, but the idea is to have the minimum cost to do all this traveling and then go back to our initial city. Here is one example of the weights or distances that we need to traverse to go from A to C, for example, is going to be 11. And going to A to D is going to be 6, and so forth. Here are the possible paths that we can choose from going to A to B, from going to B to C or to D. From starting from A, we have three possibles. Going to B, going to C, or going to D. Going to B, we have two possible paths. Going to C or going to D. And from D, we only have the choice of going to C and then going back to A. Here is our pseudocode for this dynamic programming solution. We are using a recursive function here, you will see, and this is the cost function G. The cost function G is from I to S. Starting from the point I is the starting vertex, and S is the set of vertices that the salesman will visit exactly once. So we need to get the minimum of the weight from going to I to J plus the cost of going from J to S minus S, to the other cities that other salesmen haven't visited yet, where J belongs to S, to these other cities here, and I is the starting vertex. If we consider the starting vertex A, then we have the cost of going to A to the other cities is going to be the minimum value of the weight from going to A to B, plus the cost of going from B and to the other vertices C or D, or well, if this is the case, if we're going from A to B, what about if going from A to C, or what about if we're going from A to D? So we have all these other options too. So we need to consider the minimum value of this. If we evaluate this part, which is the cost of going to B, from B ahead, we have the option of going to C or to D. So we need to consider the minimum value of the weight from going to B to C, plus the cost of going to from C to D. The cost of going from C to D is going to be consider the weight from going to C to D, plus the cost of going to D to back to the initial point. When we have his empty, we can reduce this from of the weight from going to D to A. Then we calculate this cost of going to C to D, and then it's gonna be 9, no, C to D, 9 plus 5, which is cost from going to D to A, D to A, 5. So 9 plus 5 is 14. So here we have this other evaluation, it's going to be 27, and for this other evaluation we have 22. So we consider the minimum of these two, which is going to be 22. Then if we again calculate these other two values that are here, and then we evaluate them, all of them, and then we consider the minimum of these three, which is going to be 23. Then the minimum cost is from going to all the cities. For our salesman the best path is going to be from going from A to D, then to B, then to C, then to back to A. This time complexity expands. That's why here I have 2 to the n. Expands every 2 times. I need to expand every time. Then how many times? N times. Then the complexity class for this kind of problem is considered NP hard. Then we have here find the sum of all values in a 3D array, m per n. So considering this our 3D array, when n is equal to 3, we have that we need in order to calculate the sum of all the elements in our array, we need to traverse all the elements. 3 for loops need to be considered. That's why our big O notation is n to the 3, which is bounded, which is a polynomial bounded time complexity p. Then we have Radix Sort. Radix Sort here we have an example of a Radix Sort. How does it work? For Radix Sort, we have an initial array. This initial array is unsorted, and this method is considering the arrangement or the sorting of the elements, but this is very peculiar because it uses the digits. It's gonna be first using this first digit in order to sort the elements, and this is gonna be put in a count temporarily. Well, we're gonna consider this count temporary array, and then we're gonna put all the elements according to the in the count array according to the digit where they belong. So here we have 9 digits from 0 to 9. So if the element is it ends in 2, no, for this position, for the first position, then it's going to go to the second index. And if the element ends in a 1, then it's going to be the count array in the first index, and so on and so forth. Then once we have this count array with all our elements. Then we're going to consider this other B array, which is going to have all the elements that we have in count, and then we're gonna put here 100, 150, which is in the first index of our count array. Then we have 901, 82, 12, 23, 55, and 77. See that here all the elements are arranged on the first digits, increasing, no? So here 0, 0, 1, 2, 2, 3, 5, 7. And then we do the same thing but with the 10th digit. So the 10th digit is here 0, 5, 0, 8, 1, 2, 5, and 7. So in this array count, we will put the element based on the digit on the 10th digit. So if it's 0, then the element's gonna go to the 0 index in the array count. So similarly, we found we're gonna have our B array, which is going to be this one, where it is already sorted by the second digit. Then we're going to sort by the third digit finally, and then once we sort by the third digit, we're gonna have our sorted array already sorted. Here is the pseudocode for this. The big-O notation for this algorithm is going to be considered d per n plus k, where d is the number of digits of the maximum number of digits of our array on our array of numbers a. No? Yeah, and of n plus k, where k is the base, or in this case the base is going to be 10, and the complexity class for the Radix sort is considered nd, right, because d per k is not considered. So nd, this is a polynomial bounded time complexity class with p. So finally, the brute force password cracker. For the brute force password crackers, we will have all the characters of the alphabets, lowercase and uppercase, and numbers from 0 to 9. So possible options for each of our characters in our password is up to 62. If we consider our password, the size of our password, or the length of our password, with n is going to be 8. So if we have to traverse for every element, we need to do a for loop, since it's going to be trying to guess what is the correct password. So we're gonna start this brute force. We're gonna try all possible combinations and all possible sizes. So we have to do a for loop here of our 62. That's why we have the big O notation 62 to the n, and where n is the size of the password. This is going to be taking a while. The complexity class considered for the brute force password cracker is BPP.